Good morning, everybody. Thank you very much for being here. It's a great pleasure and honor to introduce Koen Vandewal. His trajectory is I know more or less. He did his PhD in Hasselt, no, in Hasselt University with Jan Manka, I think, and then he went to work with Olin Ganas in Linköping in Sweden. After which he spent some time in Stanford with Alberto Saleo, and then he went to Dresden. So he's the spirit of a scientist. He's been everywhere, and since many years he has a group in Hasselt University, and his background is in physics. He has done a lot of work in understanding the relationship between optics and material science, and in particular optics and photonics, dedicated mainly to photovoltaics, but also to photodetectors and other applications. So it's a really great pleasure to have him. Today is the first day of his short sabbatical here with us at ICMAB. He will be staying with us for a whole month. So you would be, if anyone is interested in having a chat with him, you can just drop me a line and we arrange a meeting. So with further ado, thank you very much, Koen, for being here, and the floor is yours.
Yeah, no, thank you for having me, Mariano. Thank you all for coming. I'm happy to present a bit of an overview of what we do. And I try to go not too much into detail for the people who are maybe not so much expert in all of this. The title you can see here, what my group mainly does is make organic electronic devices and try to figure out, first of all, if it's worth making them, will they reach the performance which is required? And second, to try to find new types of devices. The nice thing is that for that, this is only one slide, which is maybe not so scientific, just to introduce the environment I work in IMO-IMOMEC, which is a research institute between the university and IMEC in Flanders, in Belgium. Within that institute, we are basically with 4 research groups which closely collaborates on organic or hybrid organic electronics. And at least here are a few people of those 40 people. And we have a chemistry department who then, very simplified, makes new materials, polymers, small molecules. They do the full characterization and are very equipped to do that. We benefit from this because we can talk to them and say, can you change maybe the absorption of this material a bit, or can you add some side chains to make it more soluble? And then often they say, no, it's not possible. But that's how it should go. We learn each other's language by now, I think, and that collaboration works very well. So that's why there's a red frame around this. This is what I'm supposed to do in my group, understand the materials further and look at if we can make some devices with it. And we have also some an engineering department who then, again, simplified, does the further optimization, and if something is very interesting, the upscaling of materials. But it flows into each other a bit. So what type of organic optoelectronic devices do we work on? OLED is the one which is the successful one, I guess, the one you can buy in media market, or I don't know, the electronic shop here, but the one which is in every cell phone now almost. So we still do some research on that, but then it's OLEDs mainly for applications. This is not our work, but this type of applications, more bio applications, very flexible OLEDs, so that they can be put close to the body for some photodynamic therapy or stuff like that. The opposite of all that OPV, we also do still some organic photovoltaics. There we focus mainly on doing with organic solar cells what you can't do with the other ones. So it's really difficult with other photovoltaic technologies to make them, for example, visibly transparent. The nice thing about organic molecules is that they have this, you can tune the absorption spectrum so that, for example, they are very weakly absorbing in the visible and very strongly absorbing then in the infrared. So it looks transparent, but it absorbs only near infrared. And then you can make a transparent solar cell, for example, to put into windows. The other thing is you can tune the band gap to where you want. So it's also very useful for indoor PV or some tandem PV, combine it with another technology. So that's what we try to focus on there. And what a big part now is the optical sensors. Very simplified. If you can make a solar cell, you can maybe also make a light detector. It's a very simple, I'll come back to that later. It's a very similar device architecture. Again, we focus on how to make it flexible. And applications of those are, again, have it close to the body in some type of patch or something like this. Or other applications are, and that's what we focus on. I'll also come back to it. To go to the near infrared, again, something which silicon or the classical photodetectors cannot do so easy, or where the materials are very expensive. If you want to detect wavelengths longer than 1,000 nanometer, so we look for polymers, and our chemists are trying to make polymers or molecules which absorb wavelengths longer than 1,000 nanometer. But I won't talk about it enough in the following slides. And then we tried to then invent some new device concept, something maybe you cannot do so easily with the inorganic technologies. Here are two examples, which I will also come back to, but just to get started a bit. For example, what you can do, and this we actually did together with Mariano, is have printed spectrometers. So this is a printed organic layer, and each of these pixels you see here detects another wavelength. So this would be a low cost, and here you see a spectrum measured by such a spectrometer. The size, well, I call it miniature. It's still the size of a microscope slide, but they should be easy to make it smaller, right? Yeah. The other thing we recently started doing, well, maybe before I talk to this is printed, but you can also deposit organics using vacuum deposition. And so then you evaporate the molecules and they deposit on a substrate. The nice thing about the vacuum deposition is you can do 20, 30 layers on top of each other without dissolving the bottom layer. And each of these layers, the thickness you can tune very precisely, because that's with vacuum deposition, it's easy. So we can tune this thickness within a 1 nanometer error margin. So here is a device which has 35 layers, I think. For a physicist, this is fun. I mean, if you can't make your own molecules, at least we can stack 35 layers of each 20, 30 nanometer. It's a simple device. It's an up conversion device. So it's basically a bunch of solar cells or light detectors. If you put enough on top of each other, they will add the voltages. They will produce enough voltage to drive a light emitting device, which is on top. And you just have to short the thing. You don't have to apply extra voltage, just make a shortcut. And then the infrared light absorbed by these will be converted to visible light. So we did a lot of effort now just before you all came in to get these movies to work. And for that, I have to play this. I just wanted to show you this. I couldn't show you. I wanted to show you that this is rather efficient. You can buy these infrared detector cards, you see. This is a material which, so up conversion, there's quite some materials who do that. Well, not so many, but there's quite some research on materials who do up conversion. Usually they work with strong laser light intensity, and they're very non-linear because it's usually a 2-photon effect. This one is linear with the way of doing it, which I just described, is linear. And if I can get this to start. So we do shine, and then you have to believe me, we shine infrared light on this. You see a little yellow spot here where the infrared detector card detects the infrared, but you see that pixel here, you have to look here where the mouse is that stack of 35 layers. It's about a 4% efficient up conversion at these low light intensities, because we are pretty good at making high efficiency detectors, and OLEDs are very efficient at light emitting. And the second video I had, I should open. It's just a shorted device. There's no extra. It costs 99 cents. Yeah, I know what I did wrong. Yeah, thank you. What should I push here now? Pay?
Yes, pay.
No, I should have used VLC. Yeah. Oof. You get only the sound like this because you didn't pay the 99 cents. Oh, here it is. That's the one, yeah. Oh. No, maybe just do VLC. This is not the one. No problem. But I should not have double clicked. I should have. Yeah. So, what I wanted to show you, because does this thing even have applications? Here's that pixel. It's 1 pixel, and so the electrodes are overlapping it's about 2 by 3 millimeter, that size. But you can immediately project the image onto it, and because the conductivity in plane of all these layers is not too high, the image is kept, so the image stays. That's basically what I wanted to show here. It will become more clear, but then you know a bit where to look by this introduction. So you see some image there. Yeah, to see properly what we're doing, we installed a camera here which magnifies this. You will see it later on this computer screen. And here's the lens system where we just project the image of this. Well, it's an evaporator mask because we couldn't find anything more interesting at the time. It looks like white light. It is white light here, but here's the 800 nanometer filter. So nothing of this gets through, only the infrared. And this is, yeah, so you keep the image, and if he moves it, you see. So it would be a nice, and it's a nice way to convert your silicon camera to an infrared camera by just putting that layer somewhere in between. Someone needs to miniaturize this stuff. We're not very good at that. This is the best we could do in a week. Yeah. That's all I will say about this up converter, because for the rest, it's 4 detectors and an OLED on top of each other. But yeah, it's more efficient in up conversion than any material out there. Yeah. Let's see if everything still works. Yeah. Okay. What about those devices? I talked about the opto-electronic devices, the sensors, the OLED, and the solar cells. What research can still be done? Because, okay, already for years we can make this, but can we make good ones? And what do we consider a good one? And where are the challenges? The next 3 or 4 slides, I wanted to say something about this. That's then also a bit the research we try to do. For OLEDs, OLEDs work very well. So what research are there still to do? In the visible, you can buy it. And why can you buy it? Because the conversion efficiency of an electron to a photon in those OLEDs, which you have in your phone, is 100%. So we can't do much better, I guess. That's what's written here, 100% electron to photon conversion. Okay, because this OLED is glass encapsulated or is in glass, actually only 30% of the light comes out, and there's a way to get it a bit more. But so in the end, OLEDs are 30% conversion efficiency from electron, which you push in, to photons coming out into air. That's for visible light emitting, and here you see the state of the art if you go to infrared OLEDs, or near infrared OLEDs. Those are interesting for all the biosensing and so on, because your body is transparent in that range, not so much in the visible. So people are doing materials development for infrared OLEDs, and you see it goes down fast. And so the 30% which we have in the visible at 650, that's just red, dark red. And then if you go to the infrared, so apparently it's not possible, or people haven't found the right infrared. emitter yet, and there's several systems. So that's something at least our chemists are working on hard to try to get it a bit higher here, around 800. That would be interesting, or 900, or even further. So that's a bit what the problem is with OLEDs, or where there is some, there's other research you can do there, but that's what we are for. For solar cells, that will take a bit longer. For that, I show you here just the current state of the art for organic solar cells, 20% efficient, power conversion efficiency 20%, as compared to silicon, which is over 25, at least on the lab scale, and other technologies. I read in many papers we are closing the gap with silicon and so on, but we're not. I mean, 25 is a big difference from 20%, but 20% is not 2%. I mean, I remember when we started, when I started at least, it was 5%. So it's nice. It was nice to see this progress. So that 20% organic solar cell, if you look at, it says here EQE. That means how many electrons come out per incident photon. So you see, for example, here at 800 nanometers, 90% of the photons absorbed come out as electrons. So you can't do much better there. Here's the band gap, and at 900 nanometer, I think it goes down, and here it's kind of high. And okay, so this is pretty good. Yeah, and these are the materials used. I put these chemical structures for the chemists in the room, so you can look at it. Just to compare with another technology which does have 25%, this is the one I could find, but it's higher now for perovskites. You see also there in perovskites, it's about 90% of the incident photons which are converted to electrons. And for organics, I would say the same. And this is reflected in, so power conversion efficiency is not only current, because power, if you want power out, it means you need current and voltage. And the power out is current times voltage. So getting current, getting photons converted to electrons, you need it, but it's not enough. You also need voltage. And that's what you see here, and it's basically the voltage you have at open circuit. For this one, it's 0.88, and for this perovskite, it's 1.18. So maybe this already makes clear why the perovskite is better than the organic. It's not so much because the conversion of photons to electrons is so bad for the organics. No, it's equally good. Maybe it could be a bit more square, but it's close. It's really because of the voltage. Well, here, just to go over the table, this current here, short circuit current, J, or short circuit density, that's basically this one integrated over the solar spectrum. So you have the solar spectrum, you convert those photons in this wavelength range for 90% to electrons. That's how you get the short circuit current. So it's even higher for this organic solar cell because the band gap is a bit lower. Here it's 900, this one is 800. This fill factor tells you, maybe that's not so important. It's anyway the same. For people who know solar cells, they know what fill factor is. For the ones who don't know, it doesn't matter because it's 0.8. So if you then multiply these three together, you get the PCE. And the reason why the perovskite has the higher power conversion efficiency is because the voltage is higher. This little 3% extra doesn't do so much. So what's the problem then with organic solar cells? This is then the band gap. I put here in red numbers. Okay, the band gap of the organic solar cell is a bit lower, but if you look at the difference between the voltage and the gap, you see that the organic solar cell loses half an EV, half a volt, while the other solar cell technologies don't lose so much. Here in this case, 0.37. So the main reason why the other solar cell technologies are better than the organic one is this voltage deficit, the difference between band gap or gap and voltage. So the amount of energy you lose per photon, which is absorbed. That's the reason why the other solar cell technologies are better. So that's something we will then look into, maybe also later in the slides. But just that you know what's the problem. For OLEDs, going to the infrared is difficult. For solar cells, voltage is a problem. And then for sensors, organic photodetectors, There's so many materials, that's nice, and that's why I think it's a good idea to have a light sensor made with organics, because you can tune from 1800 nanometer to UV. I got this from the chemist, these slides, maybe. Just to show you that you have many different possibilities. Yeah, for a detector, we also need a performance matrix. For OLEDs and solar cells, it's maybe easy. You want to know how many photons you convert to electrons or the other way around, or how many power you generate. For sensors, you could say, oh, the performance matrix is also how many photons do I convert to electrons? But you're interested there in a signal-to-noise ratio, so you also want something which produces low amount of noise. So for a detector, a light detector, you want two things: a good conversion yield of photons to electrons, and low noise currents. So the metric which people use in the literature for light detectors is what they call detectivity. And it's proportional to this conversion yield, how many photons per electron, yeah, external quantum efficiency, divided by the noise current. Proportional to that, there's a proportionality factor. So it's a number because noise is always very low. It's a picoamps, femtoamps per square hertz. So you get a number which is very high and is mainly important on a logarithmic scale. So we are interested in 10 to the 12th, 10 to the 13th, and the unit is Jones. So that's the number. Well, maybe that's why I put this table or this graph here. Silicon, and it looks a bit like the absorption spectrum of silicon. Silicon reaches at room temperature, this figure of merit, the important number, is about 10 to the 13 Jones. And you can see in the region where silicon works as detector, the organics can do almost as good. And I think if you really optimize, we can do what silicon does with organics. But nobody's waiting for a replacement for silicon. Because, yeah. Why would you need that? Silicon is not that expensive. What we would like to have is a replacement for InGaAs, because that's expensive. I don't know if you've ever looked at such an infrared camera price. Yeah, it would be nice to have that as also for up converters. It would be nice to have something here in this wavelength range. That's below 1,000, longer than 1,000. And there you see our attempts. It's not only ours, it's from the literature in general, but several are ours here. We can't do what InGaAs can. Actually, just where silicon works, we can do it, and then it's there also. So at 1,000, yeah, maybe just here. But then it gets difficult. Sometimes you read in the literature, oh, our performance is as good as InGaAs. But then they mean as good as InGaAs at 900 nanometer. But I would like to have as good as InGaAs at 1800 nanometer or 1700. But you see, it's not even, the detectivities are 3-4 orders of magnitude lower at this moment. So that's where we try to do research. Maybe there's an intrinsic reason. Maybe the chemists haven't made enough polymers and small molecules yet to absorb there. Also that I'll come back to. But, I thought it's good to know the questions in it. Yeah, for example, this is an application. If you can replace InGaAs, you could make cheaper infrared cameras. Okay, so now how do these devices work? And that's the nice thing to work on. That's why I picked those three types of devices for this presentation, because they're all the same. In the end, they're all the same device, to me at least. The basic principle of these devices, it's always a sandwich. You need at least 3 layers to have a good device. For all three, OLEDs, light emitting device, photodiodes, so sensors and photovoltaic devices. It's always something like this. You can always find this architecture in some way in these devices. You have the optically active, it's always a blend. And then I'll start with that one. It's in the middle here. So you blend 2 materials, and if it's a photovoltaic device or a photodetecting device, it's a donor and acceptor with the energy levels of those 2 materials. You see the colors chosen like this. So if you shine light on such a thing, eventually, energetically, you will end up with an energetically is most favorable for the electron to be here and for the hole to be in the HOMO of the donor then in this case, and for the electron here. So why do we blend the materials? To separate the electron hole pair and to get the electron to the other material so that it has less chance to fall back into its own hole and then go to the electrodes. For an OLED, you also mix two materials typically. There's other ways too, but in the best ones, you mix two materials, but then you choose the energy levels like this of those two materials. And you choose maybe a different ratio between the two materials. But you choose it like this. And again, energetically in this way, in this case, it's more beneficial for the electron hole to be on the same material, and that would be then the light, the emitter, the molecule with a very high luminescence quantum efficiency. You dilute that in a material where the electrons and hole transport it. But in this way, you basically can catch your excited state and localize it on the emitting molecule. Now, if you have this, it's not enough to make a device. You also want a way to, for example, for the solar cell, you want to make sure the hole goes to one side and the electron goes to the other side. And for an OLED or a light emitting device, you want that you inject holes on one side and that they cannot go through the device, so that they are stopped on the other side and the other way around. And the best way I think of doing is, and we do it, may sometimes hidden, but we always do this more or less when we make these devices, is use an N-type and P-type doped organic material. And then again, if you go to the doped material, electronically doped materials, it's again a mixture of two materials, but now you choose the energy levels like this. It's a bit of a simplified picture, but to get started, this is a good way of seeing it. Let's see, in this case, it's a positive charge doping, so P-type doping. The matrix, the host, is the one you have most material of. If you put a very strong electron acceptor in there, you don't need even light already in the dark. The electron will jump, and the energy levels are it's such a strong acceptor that the energy levels are like this, so that already in the dark, the electron jumps here, and the hole is left behind, and you have many holes there. And so that's how you make P-type, N-type, you just switch the roles. So if you do this, if you make a sandwich like this, you will always have that the holes go, if you shine light, holes go one side, electrons go the other, and the other way around too. So this is the best device architecture for an OLED and the best one for a photovoltaic device and sensor. So this is also the one we always more or less use. And the important things, but I think I told you already, so I can go a bit faster on that. At the metric then, for OLEDs, you're interested in how many photons come out per electrons in. So if I talk about quantum efficiency for OLEDs, I mean this, how many photons out per electrons in. For OPV and OPD, the opposite. And for doping, we study also doping mechanisms and how it works. I won't come back to it later anymore, but there the doping efficiency is also, you want as many free charges per number of introduced dopants as possible. But I will not talk about that later. Yeah, and actually, since it's always the same device, if you made a solar cell or an LED, the electrical measurement you do is also very, very similar if you want to then determine performance. You apply a voltage and you measure the current. If you do this, I call it OLED now, but you can do this on all these PIN stacks. If you do this in darkness, the IV curve will look like this. If you're here in this region, at the high voltages where the current all of a sudden goes up, that's when you have started to inject holes and from one side and electrons from the other side, and they meet each other in the material and start emitting light. They're not going through, and the electrons don't go all the way through. That's not why the current goes up, because the electron cannot go through because they're stopped by the holes here. So it's electrons falling into holes, and this is how you get how you make sure that every electron falls into a hole. So in this here, the OLED lights up, but you can also do this for a solar cell. If you have a solar cell and you do an IV curve in the dark, in this region where the curve all of a sudden goes up, this is what you then also have in the solar cell in the dark then, it should start emitting light. and it does. Every solar cell emits light just like an LED because it's the same device. Well, for a solar cell, you usually shine light. If you shine light onto it, you will already have current flowing when you don't even apply a voltage. That's why the whole curve shifts down. And then current comes out, depending on how intense the light is, how much light is absorbed, and so on. Then you're here. The open circuit voltage, which I talked about before, that's this thing. And if there's no current flowing, you're at open circuit, so current zero, you're here. And fill factor tells you then how square this curve is. And at this point here, where I tried to keep my pointer stable, that's where most of the power is generated. So if people say that's the power conversion efficiency, you're in this point here, current times voltage is their maximum, and you divide it by how many input power you give. So solar cells work here. OLEDs and LEDs work here. Yeah. And light detecting devices, there you don't care if it generates power or not. You just want a signal which is linear with light intensity. So you measure the current, and you can measure the current at short circuit or even apply a bit of a negative bias, which is sometimes more beneficial to get more signal or to make it more linear, the response. But in the end, that's the point I wanted to make, it's all the same device. At least for a physicist who like to make abstraction of things, it's the same. It's just a different optimization. Oh yeah, I think I went too fast. So if you increase, for example, if you increase the optical gap of the emitter or absorber, so suppose you start from a red LED and you make it a blue LED. For blue light, you need more energy. So voltage times current will be higher for blue light. So the IV curve for a blue LED will always be shifted to higher voltages than the one for a red LED. And for a solar cell, it's similar. For a solar cell with a higher gap, which absorbs less light, but in the dark, that solar cell with a higher gap, that IV curve will go up at higher voltages. Yeah, it's the same device. So for a red LED, usually people always believe me if I say, if the red LED, if you make it a blue LED, you need also a higher voltage to drive it because you need more energy. But for a solar cell, it's the same. If the gap of the solar cell is higher, you need higher voltages to get it to turn on. Yeah, that's what I wanted to say here. Yeah, so we make these types of devices, and we rely then on our chemists, and yeah, our chemists, but maybe they all say this from each other. They really focus on making pure materials. And okay, so this part is a bit about how important it is to have a pure material, always the same material, and how does it affect this blend. It's always a blend, so how does it affect the morphology? We started working recently, all these STMs, they are getting very good. And with some tricks, you can actually image, not almost, you can actually see the molecules, even in the scanning tunneling microscope images. So we use something not so typical for solar cell materials, but just something we could image very well. It's a blend of a donor and an acceptor. It's only a monolayer in this case. But there you can see how this morphology at the nanoscale or even the molecular scale, how it looks. So you see, and this was actually a pretty good, a material which was very good in converting the absorbed photons into charges. And that morphology is really, you see it packs both, have some type of order in there, but it's really, it's not a big crystal, it's really mixtures. There are some amorphous regions in there. So how important is it that you have these ordered regions? So that's the nice thing. If you have this type of measurements with the STM, where you can see how the molecules arrange, you can put it in these multi-scale models where we work with the university in Mons, also in Belgium. The group of David Belgion, they model them, they make these model interfaces. Here is an interface which would be very disordered, where you see it a bit, all the molecules are a bit random. And then they calculate a bit, the size of the interfacial state, so the one when the electron is just transferred. At the size, or how does it look? So they put a bit the charge density on these molecules. And what this cartoon almost shows is in the ordered case, when the charge is just transferred, on average, it's further away than in the disordered case. Mainly because in the case where the molecules can order, the hole in this case can delocalize, of the electron in this case, can delocalize a bit further. So that helps, of course, for the electron to get further away from the hole. So that's one reason you want these ordered domains, not too large and not too small. So that's a bit more what happens at the interface. The other thing we have been looking at recently is that stands for polymers. The previous one was small molecules. If you look at polymers, it's something I didn't know, but if you make these here is an example polymer. This is something which looks a lot like PB-TTT, but with different side chains. It's a polythiophene. This is the chemical structure, at least. There are several routes of making them. The more classical route, and if you buy this polymer, would be in this way, where you use, you use. I can easily tell it if you look at the cartoon. You couple the red part with the blue part, and normally it should be so that the red part alternates with the blue part, and that's also the most thermodynamically favorable. So you expect nicely alternating. In reality, you have these miscouplings. And actually, there are a lot of miscouplings. And we checked this again with such a STM technique. No, it's more here. Here, you should look for that. If in the normal route, you have many miscouplings, they can be identified. They can actually see them with STM, where these miscouplings are. And they can actually put numbers on how many defects is. It can be up to 10%. And then we thought, oh, maybe we should not just do blue-red in monomers, but we just should couple the blue-red monomer, already make it, and make sure that even if you miscouple, you would still have alternating. So then you can make a polymer which is definitely like the drawn chemical structure. So when we make this, indeed, with these STM techniques, you see that there's absolutely no miscoupling. This chemistry route also gives slightly higher molecular weight. And the mobility is 2 to 3 times higher. Actually, in this case, with this particular polymer, we try it now with all the polymers where this is possible. It's not always possible. And in some cases, we actually see worse performance for the perfect alternating one. So in some cases, you actually need those miscouplings. We do think it has something to do with the solubility. So that's something which is important for these. And if you make polymer solar cells, for example, or any polymer electronics, you want, besides high performance, you also want reproducibility. So these miscouplings are not good for reproducibility because you can't really control it. But with this route, it's a bit more, it's more reproducible. So these are more morphological considerations, chemical considerations. For this PIN device, which I just told you, all the layers which are in there, they're all 50 nanometer, 100 nanometer, which is shorter than the wavelength of the light, which is emitting or absorbed. So the total device is something about 200 nanometer, the total device thickness, while the light it's emitting or absorbing is 500, 600, 800, 900. So that's a fun optical problem. You can't use just ray optics, it's wave optics you need to use. And with that, we have been playing a few years ago now already. So the typical device for an OLED, again, solar cell, you have your absorber or emitter. Let's stay with an absorber. I didn't draw the P and N layers in this case. And you have a transparent electrode because the light needs to reach this layer. Usually this is a reflecting electrode, so you can pass 2 times. And if you do this with, I choose here a donor acceptor blend, which we liked a lot as a model system because it makes these nice mixed crystals. So we know a bit more or less what happens on the morphological scale. So the polymer here is PB-TTT. The fullerene doesn't absorb much. And here you see such a quantum efficiency spectrum. So it's not a very good detector or solar cell or whatever because it has 40% conversion, photon to electron conversion efficiency above the gap. And then here is basically the band gap or the optical gap of the polymer. The fullerene, that's why we don't use them anymore. They don't absorb much light, but that's this little bump here. And then here, it looks like there's a very small amount of absorption, but who cares because it's less than 1%. It's not really contributing to anything. You can't really use it. So actually, if you look deeper onto that little amount of absorption which we had here, but you put it on a logarithmic scale, the axis, you see there is absorption. And we've been looking for so many ways to make materials which can absorb 1,000 nanometer or longer. And actually, by just blending those 2 materials, you make a weak absorber, but it does absorb 1,000 nanometers, but only 1%. Where does this come from? All this extra absorption at this long tail here? It actually comes from these transitions. If you mix 2 materials, you have optical transitions from HOMO to LUMO on the same material, which would be like this or like this. But an infrared or a more redshifted transition going from the HOMO of one material, kicking it into the LUMO of the other material. You see from energetically, it's a redshifted transition. It's not very likely because the molecules are away from each other, so the chance is not high. But it does happen. And we know it's this transition because if you change the donor or the acceptor, this band is shifting up and down, and it's not there in the neat materials. So this charge transfer transition is what gives this very weak absorption here. So then we thought, okay, it's wave optics with some optical tricks. It should be possible to get this 1% absorption several times higher by coming up with a smart light trapping strategy. And the way to do it was rather simple, I would say. Instead of using this transparent top electrode, you use this partly reflecting electrode. It just means a thin metal, which is half mirror, but still also half transparent. So very simplistic if you don't think about wave optics. It's basically a box with 2 mirrors. So once the photon is in, it keeps bouncing in between the 2 mirrors until it's absorbed. Okay, it's more or less okay. It's a bit too simple. In wave optics, it's basically at the moment you can have a standing wave. So when half the wavelength fits perfectly in this thickness, optical thickness, refractive index times thickness, you have a standing optical wave. Then it gets absorbed very strongly. And with 2 metals, it gets a factor, at least in theory, a factor 40 to 60 times stronger absorbed. So that's what we did. We just basically replaced one of the electrodes with this partly reflecting electrode. And you already see, also with modeling, and the modeling is the slightly higher one always. The experimental result it looks a lot like it, is just a bit lower. You can increase the absorption. In this case, it's maybe 10 times. But the nice thing is also if you change the thickness here, the wavelength of that standing wave is longer, and you can keep going. And something where it looked like there was no response before, now all of a sudden has a response. So now, without needing any chemist, you can still make something which absorbed at a wavelength which you couldn't do with any of the 2 materials, but when you blend them and you have the CT absorption, you can pump this up just by changing thickness. So You feel almost like a chemist. That felt good at the time. And this is how, together with Mariano, we measured this. We made the spectrometer. Okay, yeah, if you make a double stick, you get the double resonance, and you can make smaller peaks and so on. This is also what you would expect with the optical simulation. So something where it didn't look like it absorbed anything, we all of a sudden have 25% conversion yield, which is not 100, but it's nice. So in this way, you can, with one material blend, basically, and you just make a thickness wedge, and that's what they did here already a long time ago. You can make the spectrometer then. That's how it was made. Oh yeah, now this part is about understanding the limitations. I told you the solar cells and also the detectors and the LEDs, what the limitations were. It has to do with the LEDs, it's difficult to get near infrared. And with the solar cells, it's the voltage. We would like to have higher photovoltage. So let's do the solar cells. This is what happens in an organic solar cell. This is energetically then, I try to draw. First you shine light, and if it's a polymer blended with an acceptor or something, this is how I imagine it. You excite the polymer. This excitation goes to the interface or is already close to the interface and is transformed to a pair, an electron-hole pair, which is at the interface. But you're not there yet because the electron can still fall into the hole here. That's then this charge transfer state, which you can go down here. You can lose it, or you can excite it directly, but the absorption was very weak. And this is what you eventually want, free carriers. But okay, if you don't extract those free carriers, they will not stay in your material forever. They will travel around, see each other at the interface, meet each other, and then decay again via such a CT state. So that's why this interfacial state is very important, because you go basically through it twice. Once you make charges, and when the charges are made and are not extracted, and they meet each other, you're again at such a state. So the feature which makes this state important is that the electron can fall into the hole. So it's coupled to the ground state, which it is because we saw it can absorb light and it can also emit light. So this is what you want, this is what you don't want. And it indeed happens, and that's why I emphasize so much that you can use a solar cell also as an LED, because it's also the same device architecture. So if you do that, if you use your solar cell, your blend material, your donor acceptor blend like this, if you use it as a light emitting diode, the emission spectrum, this is an old material, PPV, blended donor, blended with acceptor. It's a very redshifted emission spectrum as compared to pure material. So you don't see any pure material emission anymore. If you use your solar cell, your donor acceptor blend as LED. It's also a very bad LED. This is about 1% efficient. PCBM is also not a very good emitter. But that interface emission is quantum efficiency 1 in a million. So a lot of non-radiative decay. The absorption is also there. We saw it before. Here you see it again for this particular blend. So you have some subgap absorption related to this transition. And then, yeah, if you excite it directly, I also showed you in the detector the previous part. If you excite it directly, you can make free carriers. You can see this here. Here's the emission spectrum on a logarithmic scale. Here's that absorption spectrum, with this part being that CT absorption. It doesn't look like it's at the same energy. But if you know an emission spectrum of something, you can calculate for that same state what the absorption spectrum would be with a rather simple formula. And if you do that, you see that that emission really comes from that thing which was absorbing. And in the meantime, we have extended our absorption spectrum measurement over, you see logarithmic, over orders of magnitude. You can measure a photocurrent spectrum and then calculate, once the light is absorbed, what's the chance that you go out? What's the chance that you make free carriers? And you can see, okay, even here, if you excite here, where it's very, very weakly absorbing, okay, it's weakly absorbing, but once it's absorbed, it will split as efficient if you If you would excite here, only polymer, or you would excite only acceptor, or you excite this interfacial state directly, once you have excited it, splitting it is easy. And if it's a good solar cell material, the splitting efficiency is 99.9%. And for a bad one, it's then 70 or 50%. This is a better material. It's the same. So you see that the exciton splits, or the CT state splits as efficiently as wherever you excite. So it's not really a trap. This interfacial state helps to split charges, but okay, it's also the place where the charges meet. That's how you should see it. The other thing is that, so because of that, this state has an energy gap, and it's that energy gap which will then determine the electrical properties, the voltage of your solar cell. So you see here is that CT state energy split for 100 different or 150 different donor acceptor combinations. And you see, okay, if the CT state energy goes up, this interfacial energy goes up, your open circuit voltage goes up. So an easy design rule is then, okay, make sure the CT state energy is as high as possible. And then the question is, how high can you make it? Can you make it as high as the neat material gaps or not? Yeah, here is an example. It's not a good solar cell material, but it's a nice starting point. If you blend zinc PC and C60, energy levels are like this. The CT transition would be that one. You see this. This is neat zinc PC. Neat C60 is somewhere not plotted. And this interfacial absorption, you see it's almost 0.2 EV away. Or no, here, 0.37 EV away from the gap. So then, if you fluorinate zinc PC, oh, too fast. If you fluorinate it, it's known you shift the HOMO and the LUMO down, so you do expect higher CT state energy, and that's also what you saw if you look here. If you use the fluorinated version, you really shift this interfacial absorption to the blue, and you indeed have higher voltage because you have less losses in this CT process. And then you could say, okay, the next one, you completely make it disappear. Will the solar cell still work? And it really is the case like this. So in the best organic solar cells now, they are like this. They are, if you draw this diagram, we can't see this extra absorption in the gap anymore. And if we use it as an LED, it's basically neat, in this case, acceptor emission. We don't see any subgap absorption anymore. So I guess we're in this situation. CT state is the same or a bit higher, or at least still under debate what actually happens when they become very similar in energy because they couple and so on. But that's the case now in the best organic solar cells. So their voltage is as high as it can be, I guess, because you can't shift. The CT state energy is not the one anymore, which is the lowest, or yeah, it's together with the donor or the acceptor, the lowest. You can't shift it higher anymore. So this is how, this is the highest 10 VOCs you could get by just playing with the energy levels. But we could increase VOC by reducing the loss between CT state energy and real VOC. Yeah, here I plot a bit. These are called recombination losses. Because if you increase light intensity or you decrease recombination, this loss would be less. And the rest is then, yeah. So you can split this loss up in, because it's a recombination loss. If you reduce recombination, you could reduce this part. We like to split, but every solar cell technology likes to do this. We split it up in a radiative part and a non-radiative part. The radiative part you cannot avoid. This means this is the solar cell. If recombination happens, part of the recombination event will result in light emission, and part of it is non-emissive. Because the material absorbs lights, the emissive part you cannot avoid, and the non-radiative part, people like to think you can avoid this, like in every solar cell technology, and that's why silicon and gallium arsenide have now such high efficiency, because they manage to get rid of the defects and avoid all the non-radiative, get a high VOC. So let's see if we can also do this. So here I plot basically, this red line would be the highest voltage we could get for a given gap or CT state energy. And the dots are where we really are. And you can see that the dots are far from the red line, but maybe they're getting closer if you are at higher gaps. At least I see this, maybe you don't see this so clear. But then you have to believe me, these dots are closer to the red line than these. There's a lot of noise on it. Here I plot that difference. And this is the difference between the red line and the points. So that line is basically only this extra loss, the one you would think is avoidable. At least in the other technologies, removing defects, they could. In our case, we see a bit of a trend in that loss. We see that if the gap goes lower, this loss is bigger. So with lower gaps, it's more and more difficult to get higher VOCs. So this non-radiative loss is bigger. And this is actually something which every organic electronic device, also the OLEDs, struggle with. The lower you make the gap, I should see if I have a slide. Yeah, the lower you make the gap, this is old literature, and you see this every time coming back. If the emission energy goes down, the non-radiative rates go up. So quantum efficiency. So also what I showed you, the problem with OLEDs in the infrared. In the visible, it's possible to make a very high quantum efficiency OLED. In the near infrared, just after the red, it's really difficult because the non-radiative rates go up. This is typical for organics. It's something called the energy gap. Here it is, also known since the 70s. The energy gap law for radiationless transition. So at low gaps, it's easier in a recombination event. If the gap is low, it's easier to dump the energy into a vibration of the molecule rather than a photon. So what happens is that the molecules just vibrate instead of emit light. And this is because it's a carbon and not a heavier thing which likes to stay in place. So this is, some people say you cannot circumvent this, so don't even try to make OLEDs in the infrared. And this also then means don't even try to make high voltage organic solar cells, which I don't like to believe so much, but it makes it difficult. So we need to find a way to stop dumping the energy in the vibration. So somehow fix. Yeah, some people say just replace all the carbons by silicon. But yeah, so fix the carbon atoms. In all that, sometimes it's successful and there are some ways, but it's a different design principle. I see that I already spent a lot of time, so I should slowly talk. Yeah, this is so it is possible, you know, at the same gap, you see there's a general trend, but there's a lot of scatter on the data, and we're focusing on this now. What determines if at the same energy, what determines the scatter? We did a quick try, and then I'll stop after this. We thought, because everybody makes solar cells with the gap around 800 nanometer, because that's good sunlight. If you consider the solar spectrum and you use a band gap of 800 nanometer, you absorb a considerable part of the solar spectrum, but you still keep enough energy to have a voltage. And going longer wavelengths, gaps would lower the voltage, and it's always this trade-off. So usually most organic solar cell materials which are newly made are always around this 1.5, 1.4 EV here. That's why there's so many data points here. We thought, okay, if this is really true, this is all the solar cell materials we could find. Let's do something very unconventional nobody would do. Let's just take two donor and acceptor materials, but with with band gaps at higher energies. Mix the two, the CT state energy is still at high energy, so they're visible light. So for solar cells, they're not good. Why are they not good? Because the gap is high and they don't absorb much light. But we wanted to check then the voltage and the voltage losses in particular. Is this good then? And that's very good. So they have really low voltage losses and they're actually good LEDs. So it is possible with organics to have very low voltage losses here in the visible, where also the organic solar cells work. But in the infrared, not yet. This is one of them. It looks like this because, yeah, it's visible light emitting. So it's both LED and solar cell. Nice IV curve, I would say, just a low current. And so in terms of voltage losses, it does the same as the inorganics. It's equally good, but yeah, not at those gaps. So that's the problem. The same thing limits also the photodetectors, but I think I talked long enough. And that's also the last thing I wanted to say. I had 3 more slides, but I'll stop here and I'm happy to answer any questions. Thank you.
Thank you very much. Thank you. Thank you very much. Are there questions?
Thank you very much for this nice overview. I was confused. I thought that in the infrared, the problem was the noise, and it's not. It's the EQE.
No, the EQE in practical cases in the infrared, if it's about detectors, you're basically asking about the next part. No, the noise is eventually the problem. Yeah. In the infrared is the noise. For a similar reason, because you have so many recombination events in the infrared, it makes the noise higher. So even if you fix the EQE problem, which with morphology and you have the aggregated domains in the right place and so on, a bit simplified, but so that I see solved, but the noise I don't, we have to do something about the vibrations. That was my conclusion, which comes a few slides further. Yeah.
Okay, more questions?
Thank you for the talk. So I have a question. So what's the view compared to comparing this technology to phototransistors? Do you think, because in that case, you don't have an acceptor and donor, or you can combine different materials. So I don't know if you have an opinion on that.
Yeah. For now, we stick with the photodiodes. We sticked with the photodiode, not because that's the reasons are because we knew very well how to make it from the solar cells. And second, because photodiodes in this way are usually the most linear. And this is something we see that the people who use photodetectors, they want linearity. So which means linearity with light intensity. This is something with other photoconductors or phototransistors is a bit harder to do. It's also a bit more difficult, at least for us, to miniaturize, but this is only us. That's why we didn't do phototransistors. An advantage of a phototransistor could be that you can lower the noise current by applying the right gate voltage, I think. We haven't done a full analysis yet if you can actually do better than the photodiodes. There must be some fundamental limitation where which they all should obey. In the end, it's all a photodetecting device, so they should all obey eventually a similar lower limit. I don't see a reason why a phototransistor would be fundamentally having a fundamental lower limit, but practically it could be an easier way to get the lower noise currents. Yeah, but the linearity is always difficult, I think, with such devices to make them linear with light intensity. But it doesn't have to be a problem. It can be corrected in software usually. Yeah, that's my opinion. It's not a very argumented one, but that's.
Okay. Is there any other question? No, if not, well, Koen will be here for a month, so just drop me a line, and then we arrange a meeting. And with this, thank you very much for the.
Thank you.